Brute force design pattern, also known as exhaustive search, generate and test, is a simple idea whereby we try every possible solution. We'll go through some examples where you might use it, covering some important and classic computer science problems. In each of these problems, I'll explain roughly how we could use a brute force approach, stepping through some code. It's not a good idea in exams just to say, oh yeah, nah, just brute force it, get the answer. Remember to explain how you will process and return the result and not simply generate all possible candidate solutions. We will start with the traveling salesman problem in a complete graph. Because it's a complete graph, we know it's possible to visit every vertex exactly once before returning to the start, so our aim here is to find the shortest possible path. Note that it doesn't matter which vertex we start at. When we're writing our code, we can say generate all possible permutations of vertices. That's probably enough for algorithmics. We might look later at how to do this using a recursive algorithm, but it's pretty hard. So we start by creating a list of lists, which each list is a permutation of vertices, and tours, which is going to be our dictionary, which will keep track of how long each permutation takes. Now, just a word on terminology here. If we talk about combinations, we don't care about the orders in which we traverse things. So going from A to B to C is the same as going from B to C to A or A to C to B. However, you can see here that the order does matter, because if we go from A to B to C, that's different from A to C to B. So make sure we use the right words. We are going to step through the code. Here are my dictionaries. So I won't show every single permutation. We'll just start now. For this candidate in permutations, we set the total to 0. And it's important to step through the code so that we can make sure our indices don't go out of range. And it's quite easy to be just one out on loops and things like that. So if we have got a chance to step through it, good idea to do so. For each pair of vertices, essentially this is saying we get the edge between those two vertices and we add the weight of that edge to the total. So we go from A to B, which is 3, B to C, which we add 2, C to D, we add 5, D to E, we add 6. And then finally, we have to add from the start to the end, which in this case takes us to 17. And then we add that candidate to our dictionary of tours. So we know that if we do A, B, C, D, E, then back to A, we have a weight of 17. And we do this a heap of times. And finally, we return the candidate with the lowest total. Obviously, I've only done 4 there. Before we go to the next slide, pause the video and consider how would you change this as little as possible to make it a decision problem for an incomplete graph. Can you visit every vertex exactly once, then go back to the start? And the way I decided to do that was we do the same thing. We have our list of permutations and we check to see for each permutation, is it possible? So we cycle through the vertices, and if the edge doesn't exist between each pair of vertices, we delete that option from our candidates and we continue to the next one. We also add a line to check that you can get from the last one back to the first one. And then we have a line telling us how do we return the result. So if there are still some permutations left after doing this process, we return true, otherwise we return false. Next problem we will consider is how do we find a string in a bit of text. So for example, we want to find the string algo in that text you can see. And it's a good idea, I think, to imagine how you would do this without worrying too much about code. So if I'm doing this really step by step, I look at J, I'd say, well, that's not the same as A, so that's no good. I go for D, and then K, and then N. Then I get to A here, and I say, well, A is the same as the first letter. So then L is the same as the second letter, happy days. But when I get to T, that is not the same as the third letter. And so I would have to start again. I would actually have to start again at L. For some reason that hasn't worked on that animation. Who cares? We keep going, and again we'd find A works, L works, G works, and O works, at which point we will return 7. So let's try and put that into some code. I've stepped through this again, and you'll find that we get to an error, which we would probably only get through stepping through. So for I is our counter which considers every possible starting position in the text. And then we've got j, which is our counter, which is going to cycle through the string that we're looking for each time. Now I've made j greater than or equal to 0 because what I'll do, if at any point the comparison fails, we will just set j to -1, which will break this while loop and take us to the next increment for I, as in the next position in text. Then we'll say if the text of at I plus j is the string of j, because we have to increase the position we're looking at by the position of the string, hopefully that'll make more sense, we increase j by 1. And we also need to check to see, well, this was my first thought. We can say, well, if j is the length of the string, then we return I. However, that's going to go wrong towards the end of the comparison, or at the end of the comparison, rather. So I'm going to do this in two separate if statements. We're going to say if the text where I'm looking is not equal, we set j to -1. And then we also do a quick check. If we have gone through string completely, then we return I being the start position. Right, let's see how this works. So we start with I equals 0, j equals 0. While j is greater than or equal to 0, we compare these two, and because they are not the same, j equals -1, and so we increase I by 1. I've added here on the counter, where we're actually comparing is I plus j. And we're going to keep going through this for a little while, increasing I by 1 until we get to A, at which point we'll be saying j equals j plus 1. So we do that loop again. Again, I plus j, the item in I plus j is the same as j in the string and text respectively, text and string respectively. So we do the next one. Here we find the comparison fails. We set j to -1 and we go back to I equals 5. So we step back to the next comparison point. We keep going a little bit until we get here. And again, we have successful comparisons all the way through. And it's here that I realized I made another mistake. See if you can see what it is. After we make the comparison for j equals 3 and I plus j being 10, j will then increase to 4. So this final comparison here actually needs to be j equals the length of the string. Okay, because that comparison is happening after we do the successful comparison and the increment. And that will return I, in this case, 7. For the next problem, we are going to find the maximum substring sum in a set, which is to say the maximum contiguous sum in a set of integers. Contiguous means next to each other. So in the set of integers you can see here, we can take some examples. We can do 3 plus 2 minus 5 is 0. If we take from 2 to the second 9, we add them together and we get 15. And we want to use brute force to find the largest possible sum. Like the last one, this is going to be done using an iterative approach, stepping through the set of numbers in a systematic manner. I think this one is quite achievable, so try and write it yourself. Pause the video, etc. I'm going to step through. Again, we're going to think about how we would do it by hand first before we try and write code. So if I'm being systematic, the first thing I would do is take 3 on its own. Then I would do 3 plus 2, 3 plus 2 minus 5, 3 plus 2 minus 5 plus 9, and so on all the way to the end. And I would be keeping track of the largest possible sum. Then I would do all possible sums starting with 2. So 2, 2 minus 5, 2 minus 5 plus 9, and so on. Now, if you haven't already tried the code, have a go at the code now. Here's the code that I wrote, and as I pressed record, I thought, this is done slightly inefficiently the way it's turned out. And we'll talk about why. We've got candidates, which is a list of possible numbers. And just pay attention to how I've managed the counters here. So we had to make sure we go from I equals the first one to the last one. So that's the start of the sum of integers. And then j needs to go from I to the last one. And then when we're adding them together, we've set the current sum to be, and I've written this in pseudocode, so it doesn't really matter. I haven't cycled through particularly rigorously, but I have made it clear that I want to include both the ith item and the jth item, because if you were to just write this in Python, you generally don't include the last one. Now I put add current sum to candidates because when I first wrote this, I was going to keep track of the starting point and the end point. Then I thought to myself, well, it doesn't matter, we just want the actual maximum sum. In which case it would have been better to say, let the maximum sum equal 0, and if the current sum is greater than that, then set the maximum sum to the current sum. This works, it's just slightly less efficient. And we make sure we have it returning the highest value in the candidates. The next problem we consider is the 0-1 knapsack problem. The scenario is we are robbing a house and we have a knapsack with a maximum weight capacity. We see a series of items, each with a specified weight and value. Our aim is to choose items to maximize the overall value while staying within the weight limit of our knapsack. So each item is either included or not. We might decide we will take the avocado, band-aid and the knitting needles, using our capacity of 8 and giving us a value of 13, or we might decide to take these three things, which only has a weight of 4, so we would try and do a bit more, and has a lower value as well. When we're doing this, every item is either taken or it's not taken. So that means we have 2 to the power of the number of items to consider, that number of combinations. You can see the pseudocode here is actually quite straightforward. Again, we're not going to step through how to make every single combination. We just cycle through every combination, we find its weight, we find its value, and if the weight is less than the capacity and the value is better than the previous maximum value, we set our best combination to the combination and our maxed value to that value, and eventually we return the best combination. Again, we'd read questions carefully to make sure if it said what's the maximum value, we return the maximum value. In this case, I decided I was returning the combination which made the best value. The next problem is the n queens problem. Our aim is to place n queens on an n by n board so that no queen is attacking another queen. Queens can attack horizontally, vertically, or diagonally if you've never played chess before. We'll talk about a 4x4 board here just to make it easier to follow. Now, we could take a naive approach and consider all possible combinations of 4 squares. So the first would have 16 to choose from, the second would have 15, and so on. But it's obvious at least that every queen needs to be in her own column. So we'll work along each column and then choose different rows. Again, we're not going to code this one. Let's just look at the state diagram. So the first queen is being placed in that top row in one of 4 columns. Then we'll just expand partially. The next queen is on the second row, being placed in one of 4 columns, and we'll just expand one of those again, and expand one of those again. Then once we get to the end, having expanded all of these, we need to check each state to see if there were any queens attacking each other. Now note that we actually could have stopped most of these well before getting to the end of the candidate solution, since they were already not feasible. This is something we can improve using backtracking, which is an advanced algorithmic design covered in Unit 4. Looking again at graph colouring, we will deal here with the optimization problem, finding the smallest number of colours used. It's not particularly different dealing with the decision problem. Again, I'm not going to go through the code this time, just providing a brief overview of what you would do. The first thing we would check to see if the graph can't be coloured using just 2 colours, which from previous videos you'll know can be done using BFS or DFS. If we were being pure though to the brute force design pattern, we would actually do that with 2 colours. So we would start with a particular vertex and colour it both colours, and for each of those colourings, take another vertex and colour that vertex both colours. For each of those colorings, go one layer deeper, and so on until we get to the end. Then we would need to run through and check for any conflicts. Once we've tried 2 colors using whichever method, we need to try 3, then 4, then 5. In an absolute worst case scenario, every vertex would have its own color. Of course, if we knew at the start that every vertex would need to have its own color, we wouldn't try to solve the problem in this way. But that's giving you an idea of the absolute worst case, or the limit that the worst case is approaching. So in summary, we've talked about how brute force means trying every possible solution. You can see some advantages. It's very easy to understand, although it does involve writing recursive algorithms a lot of the time, which they can be quite tricky. It's correct, it gives you an optimal solution. In fact, those are pretty much the same point, and it's often used as a benchmark so that we can compare it to hopefully a smarter algorithm. The disadvantages, as we've seen, it is very, very slow, and hence can only really be done for very small inputs. In a lot of these cases, we had to generate every possible combination, which would mean storing those combinations in memory, which would have high space requirements as well. Thus concludes our introduction to brute force. Leave a comment if you have any questions. In other videos, we will see some of the time complexities of brute force to give you a preview into Unit 4. And we'll also look at some other design patterns, such as the greedy design pattern.